Multiplying, dividing, or even simplifying rational expressions is very similar to working like we did with fractions. For example, if I'm just looking at these fractions, if I say reduce or simplify and you're looking at one fraction, you think, well, they're both divisible by 2, so I'm going to reduce it and write it in simpler form. Another way you might think of it is that 4 is really 2 times 2 and 6 is really 2 times 3. And again, if I were showing all my work, these are common factors, so I really end up with just 2/3 for my simplified form of 4/6. So reduce or simplify says basically write it as factors and then cancel or reduce the common factors. What does multiply say? Well, you have the option of multiplying across and reducing, or you have the option of saying, well, I'm going to leave 2/3 as is, and I'm going to rewrite 9 maybe as 3 times 3 and 4 as 2 times 2. And again, you might not go to this extent and you might do it in your head quicker, but that's essentially what's going on. Common factors from the numerator and the denominator are being reduced and canceled out, and you end up with 3/2 for your answer. So all you're doing is basically factoring and then dividing out or canceling. How do we do division of fractions? Well, remember, you flip the second one and you change it into a multiplication problem. And once I do that, again, I'm going to go through the extent of breaking up the 15 as factors of 3 and 5, breaking up the 8 maybe as factors of, let's say, 2 and 4. And the only reason I do that is because I can see common factors from the numerator, divide out or cancel out with common factors from the denominator, and my final answer will be 5/4. So basically what we did, if we had to summarize, is basically we took each one and we wrote it as factors. So we factored the terms, the numerators and the denominators, and then what we did was we canceled or divided out common factors. And this is basically how we simplify, multiply, or divide rational expressions. The entire concept is based on the fact of being able to factor terms and then cancel out common factors. So whether they're just fractions or rational expressions that contain variables, we still go through the same process of factor, and then, let's say factored, and then we canceled the common factors. Let's go look at some examples. Alright, all we're doing is simplifying the 3 rational expressions. So I have 3 t's upstairs and 1 t downstairs. Let's start with the variables. Again, these are just monomials. I can, since monomial means this times that, I can start doing the canceling. Anytime you're canceling, the terms have to be multiplied, in other words, in factored form. So this t goes away with 2 of those t's and I have a t squared. I can say 6 into 6 goes once, and there's really a 6 times 3 here for the 18. So if I think of it like that, I'm going to be left with a 3, and my final answer is really 3t squared over 1, or just 3t squared. So all we did was we just reduced the numbers and then the variables since they were multiplied together. Here in part B, this right here is a link that I cannot touch. I cannot do this. This would be a big no because this links 12x and 6 together. So I can't break it up and say these 6's cancel. That's a big no-no. What I really want to do is factor and then see if anybody cancels. So I can factor the bottom of this, the denominator. That'll be, take out a GCF of 6 and you'll be left with 2x plus 1, and then I have a 6 waiting upstairs. And now because I have 6 times this and a 6 by itself upstairs, only now am I able to reduce these because I have 6 times a bunch of stuff. If I have 12x plus a 6, I cannot break it off and cancel it. Now when I divide things out, remember they leave off a 1 behind. So I end up with ultimately a 1 upstairs and a 2x plus 1 downstairs, and that's the reduced version of that expression. Let's go to part C. Again, if I do this, this would be a big no-no because I have a link joining them. So here's a link, here's a link. Again, those are links that do not allow me to break the 4 and the 2 apart. So the links don't allow me to cancel it. Let me go and factor things if they're factorable. And it looks like I could factor the denominator. That's going to be a difference of squares, x plus 2, x minus 2. Actually, let me do it in red. So we got x plus 2, which we cannot factor. However, the denominator we can factor x plus 2, x minus 2. And now since I have a product, something times something, I am able to break off the x plus 2's as common terms, and they leave off 1's. And so my final answer will be 1 over x minus 2. Okay, next one, part D, same idea. Always factor and then cancel. So let me write that down as a note. Factor, and then step 2 is cancel things out. So factoring the numerator, I can pull out a GCF of x, that's going to be x plus 2. Factoring the denominator into two binomials, x and x, product 2, sum 3, that's going to be a positive 2 and a positive 1. And now since these guys are multiplied, I can divide them out and cancel this guy and this guy. So my final answer will be an x over x plus 1, and I'm good to go. Again, I cannot cancel this x and this x because of the link between the x and the 1. Part E, again, common mistake here is saying, oh, this becomes an n squared, and this becomes an n, and this becomes an m squared, and this becomes an m, and that would be a big no-no because there's these links in between them that cannot be broken off. You must first factor everybody, and then you can cancel. You cannot cancel if there's links involved. So let's redo the problem. Let's say I have m cubed plus n cubed over m plus n, and my goal is to factor the top and factor the bottom if possible. The bottom, the denominator, I can't really do anything. It's just a binomial with no GCF or anything, so I'm going to leave it as is. The numerator, however, is one of those sum of cubes formula, the little parentheses and then the big one. Remember, in the little parentheses you put the bases, m plus n. And then in the big parentheses you square the first, m squared, you square the last, n squared. Then you switch that sign and you squish the two pieces together as a product, m, n. So what we used was, we used sum of cubes formula for the numerator. Now, since it's a product of two items and there is things that are identical, these two factors go away, and my final answer will be m squared minus mn plus n squared all over 1, and that's all I got. Okay, let's simplify these two rational expressions. First one is an x plus 2 in the numerator, and in the denominator is also an x plus 2. Well, x plus 2 and 2 plus x are the same. So essentially I can make them go away, and my answer will be 1 over 1, which is just 1. Because the order of addition doesn't matter, x plus 2 and 2 plus x are the same. However, for the second one, for part G, x minus 2 and 2 minus x are not the same because the order in which you subtract matters. So here's what I'm going to do. I'm going to make the denominator kind of look like the numerator. I'm going to say keep the numerator the same just by choice. And in the denominator, I'm going to factor out a negative 1. And when I do, this positive 2 becomes a negative 2. And this negative x becomes a positive x. Which is really essentially the same thing as rewriting this guy first, x, rewriting this guy as second, x minus 2. Now they look identical, and I can cancel this guy with this guy, and my final answer is really going to be 1 over this -1, which is a -1 ultimately. So x minus 2 over 2 minus x, without showing much work, is really equal to -1 because these two guys are opposites of each other. So you don't have to show me all this work. You can say if I have something like a minus b over b minus a, by going through all this work up here, the answer is really -1 because they are opposites of each other. Okay, multiplying and dividing is the same idea. You always want to factor everybody first, and then the second step is cancel any common factors. So I'm going to think of this as a product, and this denominator is a 1. So you go to each guy. Remember, all of these guys are links. You can't break them apart. So you got to go factor everybody. So when I factor the first numerator, I'm going to take out a GCF of 3. That's going to leave me with 3n minus 3. When I factor the denominator, it's a difference of its squares. N plus 3, n minus 3 is going to happen down there. And then I have a 1 in this denominator, and this is again a sum of cubes because I really have 3 cubed for the 27, so I'm going to have little parentheses and a big one. In the little parentheses, I'm going to have n plus 3 because the base of the 27 is a 3. And then in the big one, square the first, square the last, switch the sign, and squish them to get the product. So I factored the sum of cubes, 27 as a 3 cube. Now that I have these guys multiplied and they're no longer linked, I can go and get rid of common factors. So this goes away with that, this goes away with that, and the only things I have left over are the 3 and this trinomial n squared minus 3n plus 9. So I can leave it like that in factored form, or distribute the 3n and have it in the multiplied out version. Part B, again, first thing I'm going to do is change this problem into a multiplication by getting the reciprocal of the second expression. Then I'm going to go factor and then see what I can cancel. So it's really important that you know how to factor these. These binomials in the second one don't really factor, but in the first one I have a difference of squares, x plus 2, x minus 2, and in the denominator I have x and x, and a plus 2 and a minus 1 for my two factors. Now everything is multiplied, and I can go and divide out common terms. So this goes away with that, this goes away with that, this goes away with that, and remember they're all leaving 1's behind. So my final answer for this one is really just 1 over 1, which is a big 1. Alright, last one, let's look at factoring everybody and then canceling whatever we have in common, whatever factors. So I'm going to take out a GCF of 5 out of the top. That's going to leave me with 3n plus, or 2n, I'm sorry, 2n plus 3. They're both divisible by 5. Downstairs I have a difference of squares, so I have 1 plus n and 1 minus n. And over here I have n plus 1, which I can't really do anything about. And then I have a GCF here of 3, it looks like. That's going to leave me with 2n plus 3. Now I've got everything multiplied, and I should be able to cancel out common factors. So this guy and this guy go away. These guys have different orders, but it's an addition, so it doesn't matter. And the only things that I have left are 5 upstairs, and downstairs I have a 3 and a 1 minus n, and this is the factored form, which is usually what they ask for.